Page 22A. Here, there's 2, 4, 6, 8. There's only 8 p orbitals, so there should only be 8 MOs. For some reason, there's 10 drawn. There should only be 8. We'll say a little bit more maybe later about it, but for now, there should be 8. Questions?
Would that turn the second double one to an anti?
No, this would actually be on the midline. These would be non-bonding. It'd be 1, 2, 3 below, 3 above, and these 2 would be right on the midline. It'd be non-binding. We can talk about it a little bit later, but that is a mistake. It should only be 8 MOs. 10 electrons, but only 8 MOs. Any questions about lab this week? Schedule, I think you suggest the diazonium reaction. Using your amine, doing a diazonium reaction, replacing the amino with an iodo. So you get to do one of those. There are other reactions you can start doing. There's a reaction where the nitro compound, the CH2 in the ring is oxidized. So that's another reaction from the nitro. At this point you can start branching out, but I would suggest the diazonium. You do need to make sure your amine is pure. A number of you have kind of questioned if you have enough amine. We'll have to see. You certainly should probably have enough to do one reaction, and I would do the diazonium. We'll go from there. Okay? Please, we can discuss in lab. You can stop by. I think that's enough. Are there any questions about lab? The diazonium reaction, the product is not recrystallized. Instead, you do a little short silica gel column. So that's kind of a little new feature. And then you rotor back. Okay, let's see where we're at. We have, we're doing a mechanism called NAS, nucleophilic aromatic substitution. What is this mechanism also known by? What's another terminology? What's the 2 steps involved in this mechanism? Nucleophilic addition to get an anion in the ring. The anion is resonance stabilized. We'll talk more about that. After that, then what's the next step? Elimination. Addition elimination. We've done it before. We'll do it much more as we move forward. With carbonyl chemistry, we'll do addition elimination. Now when we did this, we said it was resonance stabilized. I'm not going to redraw everything, you should have it in your notes. But then we said, hey, this reaction really doesn't happen. But we showed it resonance stabilized. Let's see if I can get back to at least a portion of it. We had a nucleophile. We have to have a nucleophile to do this chemistry. Right here, we have to have a nucleophile. In an EAS, you have to have an electrophile. And we showed this adding here. Instead of kicking the chlorine off directly, we broke the pi bond. I'll draw it in a little bit better. And we got to an addition here that looked like this. Then we showed resonance. Boom. You can put minus here or here. But even though you can show resonance, we know that this reaction doesn't take place. If you try to go do this reaction, it won't work with mild heat. That implies that the intermediate is too high in energy and we can't make it over that big old hill. That's what it implies if it doesn't happen. So maybe ask, you have this already. So if we do resonance structure, we can do here and put minus here. And then we can put minus here and move these out here. And even though you can draw resonance, apparently it's just not stable enough. And so if you do a reaction coordinate diagram, how many steps did we have in this complete mechanism? Addition, elimination. I'm going to just be very brief here. We start with the starting material. We do some type of intermediate. What's the intermediate? Well, this is the intermediate. That's one thing right there, right? It's one thing. That's the intermediate anion. Okay? And then what's next? This would have to come in and kick off the chlorine, so the elimination. When you kick off the chlorine, you know, there's starting material, there's product. We get product. I'm not going to try to say which is more stable. We just come back downhill. Which is the rate determining step here? I mean, if we kind of do this, wouldn't it be something like this? It's going to take a lot of energy to make this high energy anion. That's got to be your rate determining step. From here, does it take a lot of energy to fall downhill? No, it didn't take much activation energy. Very little activation energy. So that's going to be a fast step. The fact that the reaction doesn't take place means that this is too hard to do. How can we make this lower? Well, there could be some type of catalyst, maybe a variety of ways. One way we can make it lower is if we lower the energy of the anion. If we make a better anion, then that wouldn't be as high. Then maybe it would work at room temperature or at just mild heat. How can we make it? It's already resonance stabilized. Apparently that's not enough. How can we make it even better? And we answered this at the end. What about more resonance? And indeed, if you provide more resonance and lower the activation energy for that intermediate, the reaction will take place. Well, that's what I threw on like a ketone. First off, where does the minus fall compared to where the action took place? There's where the action took place. Where does the minus fall? Ortho, para. Ortho. If the minus falls ortho or para to where the addition took place. And it turns out that's where you need a withdrawing group. Because that's where the minus falls. You need a withdrawing group that does resonance, like a ketone. That's an example. Because if you do, then you can do resonance where you move the electrons here and move these out. And you get this very nice resonance structure that looks like boom, boom. Move this out, make double bond here. This electrons move up onto oxygen, that becomes single bond in 3 lone pairs. I'm just going to draw it this way. 3 lone pairs, that becomes a minus. So there's another resonance structure, and I'm missing this methyl. There's that methyl. Additional delocalization of the minus charge should make this better. It should lower this. And indeed, we know that from, if you go to the lab and try this, the reaction now works. What's the major resonance structure here of the 4? It's this one, not because it's important, but because why?
More double bonds.
More what?
Double bonds.
It's not more double bonds. You got 3 double bonds here, you got 3 here.
Is it because the oxygen can handle the oxygen?
Would you rather have minus on carbon or oxygen? Yes. Better. And this is what we will say. Whenever you do an addition like this, nucleophilic addition, it typically will not take place unless you can put that minus charge on a electronegative heteroatom. Now that's kind of generic. Minus on electronegative, like an oxygen or nitrogen, etc. Something that can handle a minus better than carbon. Not only is it more delocalized, but now it's on oxygen. That really lowers your intermediate down, and now the reaction takes place. How do I know? Because if you go to the lab, it takes place. If this group was at the meta position, you would not be able to draw this resonance structure. You can only draw such a resonance structure if the group is on the carbon where the minus falls. What other groups will work here? Well, nitro also works. Nitro is very common. If we draw a nitro, I'll try to redo this. Boom, 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 boom. The minus there. What does a nitro look like? It's a double bond O, single bond, minus, plus. I'm going to erase here, I think, so I can move this way. If you have this, the electrons could come here and push these out. And you end up with a resonance structure that's still plus. That is 3 charges. But it had 3 charges here. And here one of the charge minuses was on carbon. Now where is the minus at? We moved that minus from carbon to oxygen. Now it's on a heteroatom. Much better. This lowers the intermediate energy. And now the reaction takes place. Nitro is a great activator for NAS. The reaction doesn't take place without the nitro there. We add the nitro, it works. We would call the nitro an activator. Does that make sense? But hold on, I thought nitro was a deactivator. For EAS. It's a deactivator for EAS because the intermediate for EAS has a positive charge. And you don't want an electron transport atom with a positive charge over here. This is NAS. It has a minus. So your terminology. Nitro is a deactivator for EAS, but actually an activator or promoter for NAS. What type of groups usually do this? Nitro, ketone. What type of groups are these for EAS? It's group 4. Group 4s are activators for NAS. By resonance. And majority of examples it's by resonance. Sometimes you can have a group that doesn't do resonance but just pulls so much inductively that it will stabilize the minus. So down at the bottom, what type of requirement does NAS have? You have to have a strong withdrawing group, ortho or para. Strong withdrawing group is typically a group 4. Nitro, ketone. Common examples. There's others. Rate determining step right here, the nucleophilic addition, the first step. Leaving groups. What type of leaving groups work here? In our example, we use chlorine. Bromine. Let me ask you this. Very important fundamental question. You have to start with broad basics, not just memorizing specific in details. In which step does the leaving group leave in this mechanism? The rate determining step, or yes or no?
No.
No. The leaving group does not leave in the rate determining step. It leaves in the elimination. Think back to SN1, SN2. In both of those mechanisms, the leaving group leaves in the rate determining step. What's the rate determining step of an SN1? Leaving group leaving, making carbocation. What's the rate determining step in SN2? Well, it's only one step in terms of the substitution. It's leaving in nucleophile and leaving group off. Both of those, leaving group leaves in the rate determining step. So in both of those, you have strict requirements for leaving group. Halogen or tosylate, your main ones. Here, because it leaves in the fast step, just about anything can leave. As long as it can handle a minus charge in any way. If you've ever seen it with a minus charge, it can leave here. Have you ever seen OH with a minus charge? Hopefully you saw hydroxide back in 3rd grade. Well, hydroxide can leave. You do not have to protonate it. If it leaves in the fast step, we will even see carbon leave here. Now with carbon, it's going to have to be stabilized somehow. Just about the only thing that will not leave here is an H. Well, they're really in line to you, but for us, an H won't leave, and a plain carbon. A methyl won't leave. Okay, a CH3 will not leave, but maybe a CCl3 would. Why? It's more likely to be minus. Okay? You don't have strict leaving group requirements. You understand why then? Because the leaving group leaves in the easy step. Okay, let's look back at the warm-up page. Does it make sense now? First one. You take this, react with sodium methoxide. You can easily replace this chlorine. By what mechanism? NAS. Is that chlorine activated for displacement, nucleophilic displacement? What activates it? The presence of the nitro ortho or para to it. Then you can do your mechanism. You can show the resonance structure. Okay? What about this? Is this activated by having a strong withdrawing group ortho or para? It's not a strong withdrawing group ortho or para. It needs to be a resonance delocalized. Okay, it needs to be a group 4 from the EAS. No, so that reaction doesn't work. Now, we will see if you heat this at 300 degrees, really heat it up, cook it up, you can get a reaction down here. Will it be NAS? No, because what's the requirement for NAS?
Group 4 from EAS. Ortho-para.
Group 4, does that have a group 4 ortho or para? Then it ain't NAS. This is going to be a benzyne mechanism. It's going to be our 3rd and final mechanism. Okay? I mean, when we gave a requirement for NAS and the requirement's not there, it's not NAS. You can't then say, well, we're going to do it like NAS. No, it's not. There's other questions down there. By the way, down here we get isomers. The benzyne mechanism can give isomers. We'll see that. Okay, here's some examples on this page. It somehow got out of order of some good old NAS mechanisms. What's your best leaving group in SN2? Fluorine or iodine? Iodine. Well, in NAS, it's actually fluorine. Fluorine's your best halogen for NAS. Why? Why are you worried about the charge? The leaving group leaving and becoming F minus, that's the fast step. I wouldn't worry about the fast step. That's not the rate determining step. What affects the rate? What I'm saying is when one's better than the other, that means it reacts easier and faster. We need to worry about this. Why does fluorine make this better than iodine? What's the first step? Addition. Why would that be better than iodide for getting this guy or that? That's SH minus, whatever nucleophile you want. Why would F make this want to attack there better? because it's more electron poor and there's more partial plus there with the F. Now why is fluorine not a better leaving group for SN2? Because in SN2, the leaving group leaves in the rate determining step. And I didn't talk about it much, but as it leaves and the bond breaks, first off, the CI bond is weaker, so that helps. Okay? We don't have more of a partial plus with iodine. Now, I may not have discussed it in great detail, but when everybody was introduced to SN2 and you were told that iodine was a better leaving group, did you sit down on a Friday night and spend an hour or two thinking, why is iodine a better leaving group? And does it really make sense? F is your better leaving group for NAS. It's more partial plus there. This guy is more like, ooh, I want to attack right there. Anybody ever heard of a Sanger reagent? It's a reagent used in biology, biochemistry. It's basically, you got an F on it with a couple of nitro groups. And it's for getting proteins to attack and do NAS and labeling. Sanger, S-A-N-G-E-R, look it up. Okay, good old fashioned NAS. Is this halogen, is that potential leaving group activated for displacement by NAS?
Yes.
Pure nitro. So the NAS, replace that with the SH. Mechanism we've done before. Down here. Ammonia, nucleophile or electrophile? Nucleophile. It's a good nucleophile, even though it's neutral. sp3 nitrogen. What do we have here? Four substituents, yeah? Really, any of them can be leaving groups, even cyano, but halogen is probably your first thing you want to consider leaving group. Which one of these halogens is activated for displacement? Chlorine. It's got an orthocyano and a paracyano. And the cyanos are group 4. You can do resonance into it just like we did with ketone and nitro. We should do it. This is the one that's activated for displacement. The bromine. You're looking over there, is that how you do it? Answer's already given. We displace it. Why is that not NH3? I mean, that was NH3. Because you have to lose an H to go neutral. What took the H? Well, the leaving group could take the H in your mechanism and make HCl. Of course, there's problems here because ammonia is going to react with HCl. In practice, you probably need to use 2 equivalents of ammonia. So one of them can react with HCl and make ammonium chloride. That's a minor detail. Okay? We'll actually hit on that a little bit later, a little bit more. This is a case where you have to lose an H from your nucleophile to go neutral. Everybody see that? You should see that in your mechanism. Down below, there's a pretty bigger compound. React this. Here's an amine. There's 2 of them, but just focusing on one. That's a good nucleophile. What type of chemistry do you propose? We don't know carbonyl chemistry yet. We don't know Michael addition yet. There's some chemistry over here that we could do later. Right now we're dealing with aromatic chemistry, so we have some blinders on. 2 halogens, which can be displaced by NAS. Is one of those activated for NAS?
Yeah.
Top or bottom?
Bottom.
How's it activated? This is para. You know, it's not like there, but there's a ketone para. And we can envision a minus being, you should do resonance structures. I can't do 10 examples. Do your mechanism, show the resonance into the group, which is required for the reaction to take place. That's the one that's activated. Show the product. You don't have to draw the whole thing. We can just sort of draw the benzene ring, kind of cut that off over there. That one's not going to be displaced. This one will. We'll have an N. Where the nitrogen now bonded there, we have to lose an H to go neutral. And so we also produce, if we just show it in a clean line reaction, what's the byproduct here? HF. Of course, that's an acid and it's a base, and you're going to have reactions there. And so a lot of times you might kind of put this in quotations that, hey, it's not going to be clean, it's going to react and do something else. Now, what's this molecule here? Of course, all is the same. That's ciprofloxacin, cipro, antibacterial. That's how it's made. They displace one of the F's with the amine, and then they, okay, mechanism, good old-fashioned NAS. Okay, product of the one below. I'm going to add a reaction to this. I'll add a reaction to that. Anybody have an answer to either one? Top one's no reaction. Why no reaction? Let's come back to it. What's the product down here? Also no reaction? What I'm trying to get at, you have to, okay, what type of mechanisms are we doing here? What are we doing when you see these reagents?
Yes.
Good. This is EAS, and what are we putting on the ring? This is EAS iodination. Does that have any limitations? Do you ever say it didn't work anywhere? We said Friedel-Crafts doesn't work somewhere. Oh, this works. This is EAS. This is EAS directing effect. Where's it going to go? Which is going to direct? Chlorine or nitro? Strongest activator, which is it? Chlorine. Forget about it. Ortho or para? Ortho or para. That's probably hindered because it's in between. You know, really possibly three products, but we get, you know, we can say maybe it's going to go ortho. I drew ortho to chlorine, para to chlorine. You know, I'm not going to draw that ortho to the other side. Okay? What I'm trying to show here is when we get more reactions, you have to address them, start out in a broader context. What are we doing? What mechanism? Okay? What's the generated reactive species here? What is this generated? I+. Remember, iodine is oxidized to I+. Is that electrophile or nucleophile? Electrophile. How do you know it's an electrophile? Because it's electron poor. And it loves electrons. I mean, okay, do you know what an electrophile is? What's the reacting species here? Okay, plus don't do anything. Okay, that's a spectator ion in anything you ever do. Forget about it. Alright? This is really what? Methoxy. Minus. Is that an electrophile? What do we call it? Nucleophile. So we're not doing EAS. We can potentially do NAS. Now we look over here. Is that activated for displacement by NAS? What's the requirement? Ortho-para strong electron withdrawing group. Do we have one?
No.
I don't see one. Ortho or para? What's the answer here? No reaction. Okay? It's no NAS.
Doc, what about at high temperature?
A what?
High temperature.
That's why I kind of went here. If you heat this up, heat it up about 300 bejeebies, it will react, but it's going to be a different mechanism. It certainly will not be NAS because NAS has a requirement, doesn't it? And that don't meet the requirement. We're ready to look at benzyne mechanism. Questions about NAS? Also known as what? Addition elimination. That's the two steps. The two primary steps. Okay? Well, benzyne, I'm going to blow your mind here. It's not known as addition elimination, but it's known as elimination addition. See, we look for these simplistic stuff that means a lot. By the way, there's an example of NAS over here used to make olanzapine. It's an antipsychotic drug. There's also a nitro reduction. There's two nitro reductions. There's another one there. Okay, the benzyne. Benzyne is another way to substitute a leaving group off of a ring, but it ain't NAS. We're going to call it elimination addition. It occurs when there's no strong electron withdrawing group ortho or para. Because, to the leaving group, because if there is an electron withdrawing group, ortho or para, you're going to do your NAS. If there is one, you're not going to do benzyne. So pretty much we can say it occurs when there is not a strong electron withdrawing group. The reason you're not going to do benzyne is because benzyne is much more difficult. You'd never do the more difficult mechanism when you can do the easier one. So what is this benzyne? First off, it does end with YNE. What does that mean? Like an alkyne. We're going to see like a triple bond somewhere. It requires partial conditions or a very strong nucleophile. If you've got a very strong nucleophile, you can actually do this at cold temperature. We'll point out what a very strong is. Okay, if you try to take chlorobenzene reacted with KOH, which is a nucleophile, maybe trying to make phenol, it ain't going to work. You cannot just displace this by NAS. Okay, certainly not SN2 and all that. But if you take and heat it with KOH at about 300 degrees and put some pressure on it, 2500 psi, this is called harsh conditions, forceful or forcing conditions. This is where you're getting mean and saying, hey, I'm going to make you react. Heat and pressure. If you do that, it will work. You will get a reaction. If you have to work it up with acid, we'll say why, because you have to put the proton on. You can get your substitution. But it ain't NAS. It's benzyne. Let's look at this. Okay. So how do you want to do this? The objective is to replace the chlorine with the hydroxide. How do you want to do this? Now, I hate to be repetitive, but do I just want to do something like that and say game over? No, that's SN2, and then do SN2 and sp2 carbons. Do I want to add that and bring this here and give something like this?
No.
Why not that?
NAS.
Because that looks like the NAS rate determining step. So what do you want to do?
Is the shoot off the seal?
Do you want the chlorine to just leave and to make that carbocation? That looks like an SN1, and you would never make the carbocation on an sp2, original sp2 carbon, unless we say it's okay, but typically no. So somebody give me another way to do it. What are we reacting this with? KOH, nucleophile, also a base. That is, it also likes H's. Well, the first step here, I'll have to go ahead and kind of show it to you. Get rid of that guy, right? This is hydroxide. First step here is this, taking this H, and I'm going to show it sort of stepwise. It may be concerted. If it takes that H, what do we get? That plus water, right? Just an acid-base reaction. Mark.
Can you have a charge on sp2 carbon?
Let's look back at this. What if you had this alkyne? Can you react that with a base like sodium NH2 and make that plus ammonia? That's a carbanion. And that is SP. And we do that a lot. That's your alkyne carbanion. That's pretty relatively easy to do, and we do chemistry with that. It's not SP, but it's SP2. Which is better, that or just something like that, which is SP3? And then that's SP. Hybridization effect. The more S character, the more stable it can be. Okay? It's 33% S. That's the only stability you can argue for it, although there's something else. I mean, that's better than this. Okay? Remember, this ain't easy. We had to really make it do something. What's in our favor? Well, it's really 2 going to 2. It's, let's see. What other stability does this have other than being 33% S? I mean, it does have this chlorine, and it's sort of pulling those electrons that way. So that's at least some argument you can make. Now, what can we do from here? Well, here, what's sort of known, this is the mechanism that's pretty much been proven. At this point, this can move in and kick that off. And what does that give? Triple bond. It's almost like any time you can make a pi bond and kick off a leaving group, that's easy to do. Well, it ain't easy in this case, but again, we're forcing it to do something. At this point, we go from 1 molecule to 2, at least 2 species. So that's driven a little bit by entropy. And what do you want to call this beast? That's a benzyne with a triple bond. And a lot of books will just show this all together, where they take the H, move those in and kick those off, a lot like an E2. Take the H, move it in, kick off the leaving group, like an E2. I sort of showed it stepwise. It's sort of either works. It depends on if this is really formed first. Okay, if this is a triple bond, what's the hybridization of the carbon here? SP. What's the geometry of an SP? Linear. Does that carbon look linear? I got a carbon that has triple bond, and then this. Does that look linear? No. Linear would be that. So is this a happy carbon? No. And it probably ain't sp. It's a wicked hybridization because it's constricted by the bond angle there. There's probably some talk about this. The second pi bond is probably not overlap of p orbitals. It's probably actually overlap of two hybrid orbitals. Okay? We're not going to get into much about this. It's a very high energy intermediate. But what have we done to get there? We eliminated. We essentially eliminate what? HCl. We eliminate HCl to get here. Elimination. Now at this point, it's symmetrical. At this point, a nucleophile will add. We have a nucleophile, hydroxide. Let's don't use that because let's just keep it one equivalent. We have water. We made that plus water. We made this plus water. Here's the water. This then adds here, and electrons come back. What does that give? We made that bond. The H's are still there. What's now on this carbon?
Lone pair and minus.
Lone pair and minus. That's what that arrow means right there. Now we said typically when you do a nucleophilic addition you have to put this on a heteroatom. Well, it's not. And by the way, there's no resonance here. Please don't think that's resonance stabilized. It's not resonance stabilized. How do you want to get to the home? Get home. What do we need to do? I think I heard hydride shift, not hydride. No. Hydride would mean we take the H and the 2 electrons. If we take the H and 2 electrons, we leave an oxygen with only 1 lone pair. We need to leave the lone pair behind. We need to take just the H, and these 2 electrons need to stay on the oxygen. Just the H is H+. We need to do an H+ transfer. Just like we've done before. And we'll do many more times. Probably intermolecular. Okay? Please don't take time to draw this, just look at it. You've got many molecules around. You know, this minus probably takes an H, leaves that behind. Where some other minus takes that H and leaves it behind. Okay? It's probably intermolecular. Ultimately, we'll do this H+. And if this H comes and moves here, that means we can take it off. Please don't write it down. Just I'm trying to show you the process here. That becomes a lone pair, so let's just turn that into a lone pair. And the H gets put here. There's 2 electrons between the carbon and the H. Let's just turn those 2 electrons into a bond. And so there you go. There's your H. It's there. Okay? There's your Benzyne mechanism. Elimination, what do we do here? Addition. We had a proton transfer step. It takes a lot of energy and heat. What do y'all think about this benzyne? Y'all believe this stuff? Any questions about the benzyne? Why does it attack there? Good question. It's a very strain. We can show a resonance structure here. What happened to my minus? Did I lose my minus charge here? Why did somebody say something? Some books will show it like this. That is, don't show that arrow. If you don't show that arrow, just have that chlorine leaving to give. If it just leaves, what do you get? A plus and a minus. And at this point, the water could add here, because it's plus. And when it adds there, but I'm doing my minus. There was a minus here originally, wasn't there? See, nothing would happen. You just have that minus down there. Basically, the overlap here is very poor. And it's sort of more like this. You'd have to do some reading. I just don't want to take the time to get into the structure here. It's a good question. If you consider this is not a resonance structure of that, but it is a resonance structure of this. This is essentially a resonance structure of your benzyne, where to show the benzyne, you would just move the electrons in and show the triple bond. But see, there's not good overlap here because of the strain. So this is a, and so that illustrates the positive charge. So am I lying to you about this benzyne stuff? Y'all believe that a triple bond can really form? Well, this was the mechanism, and some people didn't believe it. They set out to try to prove it. What support can we get? Somebody showed this. You can actually make these, and then somebody showed that if you put in a diene, it will react to give this by what type of reaction? Leaving a double bond here. So it's like it did have a pi bond. This is known. If you make the benzyne, throw in this, you can get that. That sort of supports that there must have been a triple bond there. We're out of time. Please look. By the way, I did cut. This is new. There is some discussion there of the benzyne structure. Please look at the next page at the additional proof. And why, when you do the reaction here, does some of the nucleophile end up on the labeled carbon, but some also ends up on the adjacent carbon? How do you get the nucleophile on the adjacent carbon? Please try to figure out why. We'll look at that. We'll finish things up on Friday. The test is Monday. Okay? Friday, we'll try to answer questions here in class. Okay, guys, see you this afternoon. No, I actually didn't show the water was generated.
After tomorrow, it didn't.
SM2 would be 2 quarters. Usually 1 arrow is all you ever want to use unless you know it's 2 steps.